Hi everyone and welcome to my Go course. This is a follow-along video and this time we're going to create three-dimensional function plot using Go code. I found this particular example when reading a book, The Go Programming Language, written by Alan Donovan and Brian Kernighan. That's why I decided it might be interesting if I explain to you this particular code, and we'll create a Go program that will be able to generate images like this, three-dimensional plots of functions, and I'll explain it to you step by step, and also we'll extend the code to give it more functionality. So let's begin. These kind of images will use SVG, the simple vector graphics. And in fact, what we will do will be the isometric projection of a three-dimensional objects. So if you look at this function plot, this is a plot of a function sine r divided by r, and it can be represented as a three-dimensional object, but in this case we have it on the screen as the two-dimensional isometric projection. So we can imagine a three-dimensional space with three coordinate systems, with the coordinate system of three axes, x, y, and z. And with it two-dimensional projection, we have only two coordinates, so that's why we should project all of three coordinates of three-dimensional space to two coordinates of two-dimensional space. So let's start. A few words about the SVG. SVG stands for Simple Vector Graphics, and this is the way to represent graphical vector images using the XML. So for this video, for right now, I'm just gonna create some SVG objects. So for this, you should use the XML. And usually SVG graphics are all wrapped within SVG tags. So I open and close the SVG tag. And since this is the XML, I should also specify the XML namespace attribute. And it will be HTTP www.w3 org 2000 SVG. Great. And I can also give it some style, and let's say stroke, give it the color gray, and I'll fill the background with the white color, and I'll give the stroke width 0.7 relative units, and I'll also give it a width attribute which will be 600 pixels and height attribute which will be 320 pixels. So this is the very minimalistic SVG object. It contains nothing because it only contains this wrapping tags. But SVG allows you to create different kind of shapes, figures, using lines, polygons, and circles, and so on. So I'll just demonstrate it to you by creating a simple polygon. So for this, I should write a polygon tag, polygon, and I'll close it here, self-closing tag. And polygon consists of points. This is just a set of coordinates. So every point has two coordinates, coordinate x and coordinate y. So x, it's an axis which goes from, like, let's imagine this is our plane, coordinate plane, and this is the 0 point. So x axis goes this direction to the right, and y axis goes down. So for example, let's say we would like to build a rectangle and which has the points A, B, C, and D. So let's write the coordinates of the point A. I would say the x is 100 and the y is also 100. Now this point is not drawn because it's just one single point. In order to represent something, we need at least one line. So I'll write the coordinates of the second point. So it will be, let's say, point B will have the x 100 and the y is still 200 and the y is still 100. So 200 and 100. Now we have the line, and let's go down by 100. So 200x and 200y. Great. And the very last point will be 100 will be x and the y will be 200. Yes. So, and we'll use this kind of polygons to render the surface of this three-dimensional function. And our three-dimensional space, our two-dimensional surface will consist of this kind of polygons. So, as I mentioned before, this function is a three-dimensional object, and what we do is we do a projection of it to a two-dimensional space. In the three-dimensional space, we have three axes, like x, y, and z. And in two-dimensional, we have x and y. So we should do a projection of it. And the projection we'll do is called isometric. So if I go back to here, and this is how the object will look. This is the example function we'll render. And this is the explanation of a projection. So let's imagine we have three-dimensional space, axis x, y, and z, and this is how we project them to the two-dimensional space. In our case, it's simple vector graphics. As I said, this is the sx axis and sy axis, and this angle 30, it's actually the view angle, because this is from our point of view, we look at this particular surface with the angle of 30 degrees. So we'll use it to project it. And the way to project it is actually, as you see, it's a triangle, and you can use the Pythagoras theorem, and you can use the trigonometric functions like cos and sine to know the values. As you see here, for example, the projection of x will be the cos of this 30 degrees, and y will be the sine of the 30 degrees. Great. So let's start writing some code. So at the beginning, when writing this program, we'll just generate some kind of SVG object, and we'll just print the SVG XML code to the standard output. So for this, I'll just use the FMT package and printf function, and I'll just print this SVG XML code to the standard output. So I'll just copy paste this XML here, and actually it's a good idea to split it to several lines. So I'll use this. By the way, this is the string concatenation, and I also need to print the closing tag SVG. Again, FMT print. I'll just use print ln. Yes. So far great. Why am I using printf? Is that because I would like to set these values. I do not want to hard code them. I would like to set them in the Go code. So for this, I'll create two constants, width and height, and the value will be 600 and 320. So now I can use the verb d and set these values in the function. So it will be width and height. And if I run this code, I'll see it was printed out. Yes, but so far our program does nothing. It calculates nothing. So let's extend this code and let's think how we do this. So in order to do this, we need to render this kind of surface, and the way we render it is by using the polygons. And you might think as every polygon is a cell on the plane, on the two-dimensional plane, which will be on a three-dimensional plane actually, which will be projected on a two-dimensional plane. That's why we need to think about like how many cells should we have. So we already defined the width and height of our two-dimensional projection, and let's also define the amount of cells. It will be 100, so 100 cells, x and y. And let's also define xy range. It will be 30 pixels, and it will be the axis range from negative to positive. And we'll also define xy scale. And xy scale, it's the amount of pixels per unit per cell. So it will be, let's use height, the value of height divided by 2, the half of height, and divided by x range. So far so good. And within these main function and between this SVG tags, we should print this three-dimensional plane. So let's do this. As I said, our three-dimensional plane will consist of many small polygons, and there should be a way for us to calculate the coordinates of every polygon, and the coordinates will be x and y. So for this, I'll create a function, and I'll name it corner, because every point of a polygon, it's a corner of the polygon of a rectangle, let's say. And it will accept the two integers I and j, because for every cell, I and j is the number of row and the column. This is how we address a cell, and it will return the function will return the coordinates of every corner of this corner. So the returning data type will be float 64, because the coordinate is a float, it's not an integer number. So, and in this case we should return the coordinates, and we should calculate them. So first we should find the coordinates of the point at the corner of a cell, and this is the formula to find the x. So we should take the xy range, and we should take the number of the row, because the number of the row, because there will be like within this we'll have like 100 cells, so that's why we'll have 100 rows. So we'll take the current number of the row divided by the amount of cell, and subtract the half, because it should be in the middle. So we do this by dividing by cells and minus 0.5. The thing is that this will be untyped, float constant will be truncated to int. That's why we should actually convert this integer type to float 64. Yes. And the same will be for the y coordinate. Again, we'll take the xy range and multiply by 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5 we use j. This is the number of the column divided by the amount of cells, and we need the half because it should be in the half, in the middle. Again, I'll convert it to 64. Yes. And now that we have these x and y, we should place them. We should actually think of our two-dimensional plane as a regular plane, like we use in the math, and usually we have the center of the coordinates, the beginning of the coordinates in the center, in the center. So we should place these 2 points right in the center of the plane, and the center of the plane is half of the width and half of the height. These are the coordinates of those. So for this, that's why I'll create Sx coordinate. This is the coordinate on the SVG plane, and I'll use the half of the width, so the middle, plus x minus y, and I'll multiply it by xy scale, because the output coordinate will be in pixels. That's why we should use this pixel value per unit, because this x minus y, it's the amount of units, and this is the amount of pixels per unit. So at the end we'll have the pixels. Yes. And the same we'll do for sy. We'll use the half of height divided by 2 plus, and in this case we use x plus y, and multiply by xy scale, and we'll return those 2 points as x and as y. So great, we implemented this function, and now we can create the polygons. As you remember, I created the polygons. If the polygons consists of 4 points, kind of rectangle, it needs every point has 2 coordinates, so at the end we need 8 numbers. So for every point we need to run this corner function in order to find its coordinates. So for this, I'll do this in the loop, because we should do this for every cell, and we have 100 cells, and I'll do this across the x-axis and y-axis. So it means in total we'll have 100 times 100 cells. That's why I should do this. I should do a loop within a loop, like a nested loop. So I'll define a loop, for loop, with the parameter I. I'll start it from 0, and I'll go through all of these number until the amount of cells, and I'll increment this parameter, and I'll create a nested loop with the parameter j. Also, I'll start from 0 and go through all of the cells, each cell, and in this case it's like each column, and j++. So, and within those loops, I'll find the coordinates of every point. So you should think of it that I have, if it's a triangle, if it's a rectangle, if it's a polygon consisting of 4 points, I need 8 coordinates. So for the point A, it will be coordinate AX and AY, and for this I'll call the function corner to find its coordinates, and I'll put the parameters for the current iteration I+1 and j. Why I put I+1? Because I want to start from this point. So if it's I and y, I'll start from this. This is I+1 and j. Sorry, this is I and j, and this is I+1 and j. This is I+1, j+1, and this is I and j plus 1. So I'll go back to the code. This is the code, and this way we'll find the coordinates of the A, then bx and by will be corner of I and j, and cx, cy will be corner of I and j plus 1, and dx and dy will be corner of I and j plus 1. So far so good. And after this I'll just print this polygon object, and I'll use this XML notation. So I'll just print it to the standard output using the printf function. And I forgot to put a next line. Okay, yes, here. Okay, printf. And for this I'm using polygon object. I'll close it, self-closing tag, and it requires a points attribute, and it will have 8 coordinates for every point. So every point has, each point has 2 coordinates, so in total it will be 8 numbers. And I'll use the g verb. G. So here we have 4, and we need 4 more. Okay, great. And I'll extend this, and I'll put the parameters for this printf function. Actually, here I will print a new line. So I will write a x and y, bx, by, cx, cy, dx, dy. Great. So let's try to run this code and see what will happen. I'll clear here and run the code. And as we see, the output is pretty big, so it's still writing because there are many 100 multiplied by 100 amount of cells and amount of polygons. That's why I cannot just copy it and copy paste it. So it's more convenient to run this code and save the output into a kind of file. So I'll just write out txt, and here is the file with the output. Okay, so I'll just copy everything and paste it here. So it takes a while, it's gonna take a while. Okay, now it was pasted, and what we see is just nothing. So I've just run through my code, and I've noticed several mistakes. For example, here in the XML namespace specification, I have an ambiguous W in the URL, and also in when calculating the coordinates of corners, actually it should be the very last point should be I plus 1 and j plus 1, and also polygon requires points, a point attribute, not point. So let's rerun this code and copy the output. I'll clear this here, paste it. Takes a while. I hope it's correct. That's why it's taking so long. And let's wait. Yes. Okay, great. It was pasted, and okay, great. Now it was rendered. So now we have a surface, a three-dimensional, but it's actually a two-dimensional projection of the surface, and we have cells as you see, and 100 by 100, and as you see, we started from the middle, and this is how we created the cells, like this. We rendered all of these cells, every polygon, 100 times 100, the amount of polygons. But as I said before, what we would like to see actually is kind of three-dimensional object. So that's why to have this three-dimensional effect, we should change the point of view. So we should take this plane and turn it a little bit by the angle of 30 degrees, as we discussed before. So let's go back to the code and let's define a variable angle, and it will be 30 degrees. So I'll use the constant of pi, because in Golang all of the trigonometrical functions, they work with radians, so I use pi, which is like 180 degrees, and I divide it by 6, which will correspond to 30 degrees. So great. And I'm gonna create an isometrical projection, and as I said before, I had somewhere this picture. To obtain the x projection, I need to use the cosinus function of 30 degrees, and to obtain the y projection, I need to use the sine function of 30 degrees. So I'll go back to code, and we already have the angle of 30 degrees, and I'll define the variables sine r and cos a, which will be the math sine. Yes, I should use this operator, sine of this angle, and math cosinus of this angle. Here it should be capitalized. Yes, and I should use these variables. I'll use these variables to project these values. So that's why for the x, I'll use the cos, and for the y, I'll use the sine. Okay, let's run the code once again and copy the output. I'll clear this, paste it. It takes a while, as always, because it's correct. But let's see. There are many polygons, 100 times hundreds polygons, and that's why it takes pretty much long to render those polygons. I'll just reload the page again. Wait. Okay, I refreshed the page, and now I'm gonna clear this and paste the output of the program. It's taking a while because it's rendering all of those tiny polygons, but now it should render them with as in isometrical projection. So we'll wait a little bit for it to be rendered. Okay, now it got pasted. Yes, great. And now we see the plane we saw before, and now it's kind of turned to the side because now we have kind of different point of view with the angle of 30 degrees. And I would like to increase actually the size of the plane. So instead, for the XY scale, I'll use the width, and I'll regenerate it. So again, copy and paste the output. I just want to make it bigger, that's why I used a bigger value for the XY scale. And XY scale, it's just the amount of pixels per unit, per cell. That's why now when rendering this, the size will be bigger, the size of the plane will be bigger, and you'll see it in a moment. But for now, let's wait a little bit for it to be rendered properly, correctly. Great. So now it's bigger, and now you can see all of those tiny polygons with their A, B, C, D points. Great. And now actually this is the three-dimensional surface projected on the two-dimensional plane, and now we can use it actually to render some functions. So let's go back to our code and let's define a function, and for this we'll use the go function. We'll call the function z. It can be anything like sine or maybe exponent, but I'll use the function from the example, which is the sine divided by argument function. So this function f will accept the x and y coordinates as floats, and it will return the value, the float 64, I'm sorry. And since the sine function accepts one argument, that's why we need to combine these two values into one argument, and that's why I'll use instead the length of the vector, or the distance from the point xy to the center of coordinates. And we can actually calculate this distance by using the Pythagoras theorem, but Go has the a function in the math package. I'm going to use it. So math package and the hypot function, because as you see, it makes the calculation according to the Pythagoras theorem. So I'll just use x and y, and I'll return the value of the math sine r divided by r. Okay, so and now I should use this value somewhere. Now I should, since this function, the value of this function will be projected on the z coordinate, there should be a way to project it somehow on our two-dimensional plane. And if you check the picture I showed you before here, in order to project the z function is projected, it actually goes, when you project it on the two-dimensional plane, it actually goes the opposite direction from sy axis. That's why what we should do in our code, here is the projection of the y, and it goes into opposite direction. That's why we should just subtract it. So we should just subtract the value of this function. So let's just calculate it. I'll define the value of z, and it will be the result of f from x and y. So, and as I said, it goes the opposite direction as the sy axis. So I should just subtract it, z, and I should also multiply it by some scale value. We do not have the scale value for the z. Let's just define it as a constant. So I'll use the I'll just call it z scale, and it will be the height, but the height is too much, so I'll use the 0.4 factor to make it less. And here I'll just multiply by the z scale. So far so good. Let's run the code. And let's copy the output of the program, and I'm gonna paste it here. So what we're expecting now, what we're expecting to see on this SVG viewer is actually the plot, three-dimensional plot of this function, but projected on the two-dimensional plane. So we should wait a little bit until it's rendered. And this surface of this function will consist of those tiny polygons. Yes, great. So now we obtained this thing, and we can play around a little bit by changing some values. For example, we can change the size to make it bigger, 1200 and 640, like twice bigger, and regenerate it. And I'll copy paste it once again. So what we expect now is to see basically absolutely the same plot, the same function, the same surface, but twice bigger. So let's see. We should wait a little bit. Okay, it got pasted, and now we see it. So I'll just scale it down a little bit. So here it is. Great. So here we have the plot of our three-dimensional function, but what we did before was actually we just printed out this SVG text, SVG XML text, and this is not very convenient. That's why we should have some kind of different delivery mechanism in order to work with it, in order to make it more convenient. And the author of the book suggests actually using the web as delivery mechanism. So for this we can do it like this. We can start a web server that will be listening on the port and serve the GET requests and so on. And once we do a GET request, we'll receive this figure rendered. So for this, let's just start. In the very first video, I showed you how to start a very simple web server in Go. So the way we do this by using the HTTP package, which provides several functions, actually many things. And I'm going to use the handle function. Handle function accepts the path for the handler as the parameter and the handler itself. So I'll just gonna write it here straight away without defining it somewhere else. And I'm just gonna copy and paste all of this, cut it and paste it inside of this handler. And I do not want to print it out to the standard output of my operating system. Instead, I would like to store the value of this SVG text as the string. So that's why instead of printf function, I'll use the sprint function, which returns a string. So I'll store it in a string. And same here. I'll concatenate it. Just add the value to the string, and same here. Printf. Doesn't look really good, but I hope this code will work, and for the sake of this video, this is okay. So now we have the value of this text as the string, and now we can set it to the response. We can send it back as a response. So for this, we use this response writer object, and response writer object implements the write method. So first we should say that the request was successful, and we should give a successful response code. So for this we use the method write header, and I can just write 200 as the OK code, but for this sake Golang HTTP package has some predefined constants, so I'm just going to use status OK, which is also 200, but it looks more meaningful and more understandable. that the status is okay and not just any number, even though it's the same number. And I will write the value of this string, but this write function actually accepts a byte array, so I'll just convert this string to a byte array. Byte array should be like this, right? Oh, to a byte, to a slice of byte, yes, like this. This is the right notation. So if I run this code, once again, actually before running it, I should start the web server. So here we have our handler function, and let's make Golang, this HTTP server, listen and serve. And here I should write the local host and the port I wanted to listen to, and new. And let's run the code. It's hanging, seems to be okay, normal behavior, because it's expecting requests. So I'll write localhost 8080. And many things happen, but it's hanging. Nothing really happens. Okay, we just have the output as a text, which is not correct. It's because we do not expect an HTML page, so let's extend our code with some HTML markup. And so for this, I'll just define it here. Here I'll use the concatenation. I'll just add some HTML text like doctype HTML. I'll just copy paste this, and then I'll open the HTML tag, and at the end I will close it, and I will also create a body tag and close it right before HTML. Close. Okay, I don't know if it's mandatory to have a head tag. I'll just create it, head, and close it straight away, head. And actually let's give it a title 3D plot. Okay, let's stop and rerun this code. Okay, now we started the server once again, and now I'm gonna hit the server, this address. Seems like it's generating. Now we see the title is 3D plot. Yeah, great, we got our SVG graphics. So this video is getting on the long side. What you can do actually is you can try to get some request parameters and to set them dynamically, for example the width and height, or scale, or maybe you can actually use a different function. For example, you can change the function here, let's say like this, and I'll rerun it. So you can play around a little bit, and as I said, you can try adding some parameters like scale is equal to 2.5, for example, and cells is equal to 200. So you can try to play around and work with those parameters as an idea, but for this video I think it's fine, and I hope you enjoyed it. Hit the like button, subscribe to the channel for the future updates. There will be more lessons, theoretical lessons, there will be more follow-alongs, and thanks for watching, and see you in the next one.